In section 2.4, we're going to talk about the symbolizing the composition of molecules using molecular formulas and empirical formulas. And then we'll talk about how to represent the bonding arrangements of atoms within molecules. Okay, so the first thing here is we have our molecular formula. This is a representation of a molecular compound which consists of the following. We're going to have the chemical symbols from the periodic table we talked about before, and we're going to have subscripts after the symbols to indicate the number of each type of atom in the molecule. So the subscripts are usually omitted, like we don't put 1 in there as a subscript. Those are usually omitted, and we assume that there's only one of them. The second part is a structural formula, and this actually shows the bonds that are formed and how it's actually arranged. Let's see some examples of that. So here we have our molecular formula. We just have our chemical symbols, and we know that there are 4 hydrogens for every 1 carbon in this guy. Here we can see that carbon is the central atom. It's making 4 bonds to each of these hydrogens. Here we can see this represented in 3D with actual sticks representing the bonds. And then here we have this space-filling one that kind of shows that those bonds are actually due to the overlap of the atomic radii. You're going to see a lot of chemistry represented in this form if you continue to go on into organic chemistry. So many elements consist of discrete little individual atoms, but some of them like to form more complex structures. So a lot of the classic ones are diatomic. So you're rarely ever going to find a loose hydrogen atom. You're always going to find H2, N2, O2, F2, chlorine, bromine, and iodine. These guys are always going to want to find another element nearby, another atom friend, and pair off. Sometimes it's even more complicated. The most common form of sulfur is actually S8, where it forms this kind of twisted ring structure. Here's an example of what the difference is in really the subtle ways that we write things. So if I wrote just a capital H, I would mean 1 hydrogen atom. If I put a 2 in front of it, I would mean 2 individual hydrogen atoms. When the 2 is a subscript after that H, I mean 2 hydrogen atoms that are actually bonded together, forming 1 molecule. Putting a 2 in front of that with the subscripts means I have 2 hydrogen molecules for a total of 4 atoms. Empirical versus molecular formula. So the empirical formula indicates the simplest whole number ratio of the number of atoms or ions in a compound, whereas a molecular formula indicates the actual numbers of atoms of each element in a molecule of the compound. Here's my example down here. If we have benzene, the molecular formula is going to show that every benzene molecule is made out of 6 carbon and 6 hydrogens. But to get the empirical formula, what I'm going to do is I'm going to find the least common multiple here of 6, and I'm going to divide both of these by 6. I'm going to just get CH. Another example would be acetic acid. Here's our molecular formula. You can see each one of these subscripts is divisible by 2. If I do that, I get CH2O. Picturing benzene here for a second, we have this ring structure here, and we can see that the molecular formula indicates all the atoms that would be in this structure, whereas the empirical formula just represents this small piece that is the smallest repeating unit. You can see that the empirical formula describes the piece that's being repeated over and over again as we go around this ring. Here is our example of acetic acid. We can see this structural formula here, and that is going to be the component in just distilled white vinegar. So isomers. It may be possible for the same atoms to be rearranged in different ways. Isomers, compounds with the same chemical formula but different molecular structures. And so an example that we're going to use is going to be acetic acid and methylformane. They both have 2 carbons, 4 hydrogens, and 2 oxygens, but they're arranged differently. So let's take a look at that. Here we can see acetic acid. We have this central carbon here, 3 hydrogens on it. That's bound to a carbon. Here we have the central carbon, 3 atoms around it, but that's instead bounded to this oxygen right here, which is then bound to this carbon. So even though they contain the same kind of atoms in both, they are structurally arranged differently. They're going to have very different properties because of that. Spatial isomers. So this one's a little tricky. In this case, we have the same kind of atoms. They are actually, for the most part, arranged exactly the same way, except for what they are is they're actually mirror images of this. You could think of this like how your left hand is very similar to your right hand, but they're not superimposable. They're not the same thing. Your left glove doesn't fit on your right hand. And what winds up happening when you turn them back around is, if you pay attention right here, we have this hydrogen that's sticking up towards us, where in this example, that hydrogen is actually sticking towards the back. And even though this is a subtle difference, it can actually lead to some pretty substantial differences in properties. A lot of medicines and things of that nature have these properties, and sometimes they can be very medicinal, and other times they cannot. One famous example was with a drug called thalidomide. It had a property like this. It had both an S form and an R form. The S form was found to be helpful to women when they were pregnant to avoid morning sickness. And but when they went to distribute it in order to save costs, they left the R form in there as well. And it turned out that the R form actually led to birth defects. So it's very important to recognize these sorts of things, and always be very careful with any kind of product that you use in order to figure out, whether or not it's safe.